So each tau s plus 1 term will contribute to the minus 1, because when you equate the denominator to 0, so each term will contribute to a minus sign. So therefore, the sign of g of s will be negative if the number of terms are going to be odd, and if the if the number of terms are going to be even, then the sign is going to be positive. That is what they are saying. So if g of s will be negative for s more than the odd number of poles and zeros. So if there are odd number of poles and zeros, g of s will be negative. It will be on the negative side of the real axis. So if there are even number of poles and zeros, then g of s will be positive, and it will be on the positive side of the real axis. So we don't bother about the complex poles or zeros which are going to occur in conjugate pairs, because they are not going to play any effect here, because they are not going to lie on the real axis. They are going to lie in between the space of the real axis and imaginary axis. So this is rule number 2. Now rule number 3, if the number of poles exceed the number of zeros by 2 or more, then you have to find the distance between them. So that you have to see to draw the graph. They are saying find the number of poles and number of zeros. If the number of poles are more than the number of zeros by 2 or more, greater than or equal to 2, then the average distance will be independent of k. So they say the distance is going to be independent of k. So if you consider the polynomial which is going to have all the powers from n to 0. So this will be the polynomial. Now we will take the ratio of each leading coefficient to the sum of L of s. Okay, so you're going to find the distance, and you're going to see whether that is independent of k or it is going to be dependent on k. So I'm going to write g of s equal to p of s by q of s. It is a rational polynomial, and I'm going to write p of s equal to q of s plus k into small p of s. So if the order of g of s exceeds p of s by 2 or more, then you can say the average distance is going to be constant. So mathematically, how I'm converting this rule into a mathematical equation, that is what is given here. The next one, when will the root locus go to infinity? So the angle we have to find, so that angle is given by rule number 4. As k tends to infinity, the pole 0 branches will head off to infinity at some angle given by theta n is equal to 2n plus 1 into 180 by p minus z. So P is the number of poles, Z is the number of zeros, and N is going to be which pole I'm going to consider. So you can see here, if there is a pole or zero here, definitely it will branch towards infinity at some angle. So what is that angle? That angle is given by this formula theta n. That angle is given by this formula. Okay. So from the equation, you can say that n will vary from 0 to p minus z minus 1. So you know p is the number of poles and z is the number of zeros. So the angle can be easily understood from the figure. So the some test point is going to be far away from the poles or zeros. So I'm going to draw a line from the test point connecting the pole or zero, and I'm going to measure the angle. So each pole will contribute an angle of minus theta, while each zero will contribute an angle of plus theta. So effective angle will be z into theta minus p into theta. Okay, number of poles is p. The total angle is minus p theta. Number of zeros is the z. So the total number of zeros is z into theta. So the effective angle is z minus p into theta. But we say that if the total phase angle will be odd multiple of 180. Okay, it has to be odd multiple of 180. So z theta minus p theta equal to 2n plus 1 into 180. Or from this I can find theta n is equal to 2n plus 1 into 180 by z minus p. 180 or minus 180, we don't feel the difference, because as long as the angle is an odd multiple of 180, the sign is not going to be any issue for me. So next one is I'm going to find where the intersection will happen for the root locus. So I'm going to define a centroid point given by z equal to summation of real poles minus summation of real zeros by number of poles minus number of zeros. So add all the poles, add all the zeros, real poles and real zeros, subtract them, divide by p minus z. So this is going to be the point on the real axis where the root locus is going to branch forward.